Hi, everybody. Welcome back to Econ 152, Economics of Education. As promised, I wanted to go over the two midterm short answer problems that were in the assignment in the midterm we took, looking at reviewing chapters 1 through 7 in the Levenheim textbook. So I'm going to go ahead and do that with you today. The first one is pretty straightforward. For those of you who've already taken 140 or in 145, it should be a review. For those of you who are less familiar, this comes from the question about the empirical evidence we use in economics and to study education policy. And so it asks you to write out the bivariate regression form or the simple regression equation of a model hypothesizing that school S has an effect on earnings, a causal effect on earnings. And this is a common assumption we make, right? More school, better earnings, whether it's human capital or signaling theory. And so I ask you to write out the form, identify the dependent and independent variable, and then say what kind of bias this model might be subject to. And so for those of you who are kind of floored by this problem, the first step is just that we're going to draw or write out a regression equation. And remember, a regression equation is basically slope-intercept form. We're looking at the marginal effect of a change in x on a change in y. In this case, our x is years of schooling and our y is income, y. So I write it out as y equals alpha plus beta 1 s plus some error term. And so in this case, y is income, and it's a function of some constant, and then some coefficient attached to years of schooling, and then some error term that collects everything that's not explained by years of schooling. And so we're saying that income is a function of years of schooling and some other stuff. Ooh, over there, other stuff. You could also write it out with any letter as a variable, right? So you could use any other Greek letter. You could do beta naught as the constant and beta 1 as the coefficient for s, right? That's still perfectly functional. If you used other variables, that's fine too. The main thing you want to get at is defining those variables. And so because y is a function of years of schooling, it is the dependent variable. S is the independent variable because it's the x. It's the thing that's causing the y. What's being caused is income. Changes in income are a function of that education, that years of schooling. And then, so we've got that our y is dependent on years of schooling. And then beta naught or alpha is our constant. And the beta 1, or whatever that coefficient is going to be our marginal effect of s on y. And then e is just our error term. And you could also use mu or any other variable, any other Greek variable. So let's see, does that work? Cool. Hopefully that makes sense. If not, let me know. Regression equations are used really, really commonly by economists. So you'll see this versions of that, more complex versions of that same equation in journal articles and textbooks all around economics, not just in economics of education. The last question asks what bias this model is most likely guilty of. What I was looking for was omitted variable bias. If we're trying to explain variation in income, education explains that. But it's not the only thing. Lots of other things tell us about a person's income, determine a person's income. So think about your own self. The years of education you have, having a high school diploma or an AA, get you to a certain level of income. But those aren't the only factors. Your experience, your age, maybe other factors have a role to play in how much money you make. And so when we only have one explanatory variable, we're always going to be guilty of omitted variable bias because nothing on earth is explained by just one thing. So we always want to look for omitted variable bias. A lot of people put down selection bias. lots of studies are guilty of some kind of selection bias. A truly random sample is really hard to get. That's why we like a really large sample, so we can help correct for some of that. Some people mentioned ability bias, and we want to remember ability bias is also a bias, but it's built into more how different levels of schooling can have different effects for different individuals. And so that's not exactly what I'm looking for. It doesn't exactly fit. It is relevant to our discussion and a bias we've discussed, but it's not exactly what we were looking for. If you think you had another bias that was built in that makes sense in your exam question, please let me know. But the main thing we're looking for here is if you try to explain wages with just education, you're going to be missing something. You're going to be piling things like years of experience, whether or not you're trained in that field, whether you're at the entry level or not, demographic stuff like race and gender. All of that just gets shoved into the error term. And that's a bias, that we're not explaining that. So that's one of the problems. Education is not the only determining factor, it's one. So that was that short answer problem. The extra credit question asked about the empirical evidence about school quality and returns to education. The short answer is better schools do seem to show higher returns in terms of wages to education. So higher quality schools, depending on how you measure that. Lots of people wrote lots of interesting things. If it was relevant to class, something we discussed, you got some points for it. The more points, you get more points for extra credit for a better answer. The last problem is what we're really here for. We're here to talk about number 38, which was asking you to graph a budget constraint and an isoquant curve for a school looking at producing educational achievement using teachers and computers. So I'm going to try and graph that on paper and show you what we came up with and talk about that one. So let me get some paper going. So question 38 says to consider a school that produces educational achievement A using teachers and computers, T and C. And so we can think of that as being the same function we looked at in class, where A is a function of some combination of teachers and computers. And then we get a budget constraint right here that shows us the relationship between our revenue of $8,000, the cost of teachers, $50 a teacher, and the cost of computers, which is $40. So the first thing we want to do is graph the budget constraint with computers on the x-axis and determine the slope. And we've done this in class together, so it should be pretty straightforward, but you want to think about this as being just like any other constraint, a budget constraint for consumer behavior or a budget constraint for firm behavior, right? Or a PPF, right? We're using the input of revenue to purchase either to make teachers or computers. And so we know we're going to have this graphed in XY space, and that computers are going to be on the Y or on the x-axis, and teachers are going to be on the y-axis. And that means that when we go through and solve things like the slope of the budget constraint, we want to remember that teachers are going to be that y and computers are going to be our x. And so you can do this manually. And so what we would do is we would just take that budget constraint and go through and say, okay, $8,000. All right, sorry about that. A little bit of a change of venue here, but I wanted to kind of finish this, so we're going to go a little bit quickly. There we go. So where we're at is we've got our budget constraint of $8,000 minus $50 per teacher and $40 for a computer, which tells us the price of those two inputs. So all of our money is going to be spent, all $8,000 of revenue is going to be spent on teachers and computers, and those are the prices. With teachers on the y-axis and computers on the x-axis, we know that we want to solve for y in terms of x. And this gets back to this idea of dependent and independent variable. Not in this situation so much, but that helps us just find that slope. So what you do is you go ahead and solve for t in terms of y, or t in terms of c. So we find out that if we divide both sides, subtract 40 computers from both sides, or $40 per computer from both sides, and then divide both sides by 50, you get one teacher is equal to negative 40 over 50 computers, subtracted from 160. And so what you get is that the budget constraint slope is the ratio of those two prices. And I think sometimes the easiest way to find it is to solve for it, so you make sure that you get the price of computers over teachers and not vice versa. Some people mixed it up. It's not the end of the world. And so then we have our budget constraint of $8,000 spent on either teachers or computers. We have a slope that is equal to negative 40 over 50, which can simplify down to negative 4 over 5 or negative 0.8. Whatever you put down, those are all great answers. And so you can write that out. And then the other thing you're going to want to do is put your endpoints on your graph. And to do that, you just say, okay, if I spent all $8,000 on just teachers, how many teachers could I hire? Well, to find that, you just divide that $8,000 revenue by the cost of a teacher. So if I'm going to try and spend all of my resources on teachers, and teachers cost $50, what's 8,000 divided by 50? That's the maximum quantity of teachers, 140. Is that right? 160, sorry. And then for computers cost $40 each. I have $8,000 to spend on $40 computers. So if I want to buy all computers at $40 each, I can buy 200 computers. And so you can enter those endpoints in on your graph, and that is really going to help, I think, with the understanding of what's going on. And so now, your budget constraint is really similar to a PPF, right? I have $8,000 that I can spend on either teachers or computers. If I only hire computers, I can hire 200 computers, or I can hire 160 teachers, or any combination along that budget constraint, right? So that gets us through part A. We've graphed the budget constraint, and we have the slope of the budget constraint. Now we want to solve for the isoquant curve associated with the production function. And we have a slope given, and that's where the exam problem broke down. We solve this problem the same way, whether we're looking at consumer behavior, firm behavior, education policy, anything. The budget constraint is always going to be there. Where there's a constraint. There's always a constraint, and that's because of scarcity of resources. We can't spend more than 24 hours in a day working or studying. We can't spend more than our income on goods and services, right? We can't spend, we want to minimize our expenditure relative to our production. And so with education policy, we're looking at a school budget and maximizing educational attainment. And so the educational attainment is represented by an isoquant curve, just like we would see in firm behavior. The problem is I didn't give you guys a great slope. The slope should be in terms of computers and teachers. The T and the C were left out. So I'll show you how to do that. A lot of people worked through and made do. You get points for whatever you did. As long as you put something down, you get points. But we'll go through it now. So the slope of the isoquant curve is MPC, or the marginal productivity of computers, divided by MPT, the marginal productivity of teachers. And that's going to be 2 computers to 6 teachers, which you can simplify down to 1 to 3 if you want, or you don't have to. I don't, and I just go ahead and solve for the slope of the budget constraint, negative 40 over 50, or negative 4 over 5, equal to negative 2c over 6t. Since they're both negative, the negative signs cancel out. And then what I did was I solved for computers in terms of teachers. So what I'm going to solve for here in this example is I'm going to try to isolate C. You can do it either way. You shouldn't get too much of a difference. There might be some rounding error. But what I'm going to do is I'm going to multiply 6t, the denominator, by both sides. And so I'm going to get negative 4.5 or 4 over 5, or negative 0.8 times 6t is equal to 2c. So it's I kind of messed up there, but you can see if I take the original ratio, negative 2c over 6t is equal to negative 4 over 5. Negative 4 over 5 is equal to negative 0.8, negative 0.8, and then I multiply both sides by that 6t, and so I get it away from here and stick it over here. Oh, that's not a 6, that's a c. All right, off to a great start. Better? Better. So then you just go through and solve, and then you can plug what you get for c into your budget constraint. So negative 0.8 times 6t gives you 4.8t equal to 2c. Divide both sides by 2, and you get 2.4t is equal to c. Make sense? Basically? Plug that into the budget constraint, and I've got $8,000 that can be spent on $50 per teacher plus $40 per computer. But now C is also equal to 2.4t. So I use that 2.4t, and now I can solve it out in terms of t. So now I have 50t plus 40 times 2.4t is equal to 8,000, and then I just solve for t, and that tells me how many teachers I want to hire. So 40 times 2.4t is going to go ahead and give me 96t. 50t plus 96t equals 146t, which is equal to 8,000, and then I divide both sides by t, and I get t is equal to 54.79, or let's just say 55. So I want to hire 55 teachers. I have $8,000 to spend on $50 teachers and $40 computers, and I want to hire 55 teachers to maximize student achievement subject to my budget constraint. Then I can go ahead and plug that in again. Now I have 50 times 55 plus 40 times c, and then you can solve for c, right? And I've got $8,000 to spend on computers. I'm going to spend 50 times 55, $2,750 on teachers. How many $40 computers can I buy? About 131. And so that means, oops, I'm messing up my numbers here. I'm going to have to write it again. $8,000 is equal to 5250. Oh, all right. So 50 times 55 is 2750 plus 40c. Subtract the 2,750 from both sides, and I get c is approximately equal to, all right, I'm getting all messed up here, y'all. I'm trying to go fast, and it's not working. Solve for the number of computers I would buy. I'm going to get that c is approximately equal to 131.25, which I'm going to round to 131 computers. So if you didn't follow that, oops, check this out, and hopefully that helps. And so now we have a quantity of computers and a quantity of teachers. It's not perfect. If you reinsert 55 computers and 131 computers and 55 teachers into the equation, you get $7,990 spent. So there's $10 left. With $10, we can't really buy a computer or a teacher, so there's a rounding error there. We probably need to hire, 1/5 of a teacher, an adjunct, something like that. But that gives you a sense of what we're trying to do. It gets us close enough for our purposes. And then even if you didn't solve the problem, you could always just draw a budget constraint or an isoquant, even without that, you can just pick a spot and draw an isoquant. We're not going to do the calculus for it. So the isoquant is just a curve that is convex towards the origin, right? It's cupping out, and that represents every possible level of a level of academic achievement with different combinations. That was the hardest part of the exam, I think, I'd argue. The last two parts ask what would happen if you got a higher budget. If your budget increased from 8,000 to 12,000, then you would see the entire budget constraint shift out to a higher level with the same exact slope. So that would be the budget constraint for part D of the exam. Is that right? All my papers got mixed up just now, which is exactly how I wanted this to go. There it is. So part D, what would happen if the school faced increased budget constraint? The slope would shift out. The budget constraint would shift out, the slope would stay the same. What would happen if computers got cheaper? If computers got cheaper, that would be a decrease in the cost of computers. That would rotate the budget out so that you could buy more computers at every price. But it would also increase consumption of both. If we assume both teachers and computers are efficient, yes, that new, let's see, did I draw it here? I'll draw it here. This is another example of the exact same problem I did and I went over differently. This would be if the price of computers went down. If you look on this one, if the price of computers goes down, that endpoint with teachers at 160 doesn't change, but the maximum number of computers you can buy does change. And so that budget constraint shifts out. Yes, you'll buy more computers, but you'll probably buy more teachers too. It will change the mix. It'll make it a more computer-heavy mix of teachers and computers, but you'll probably increase consumption of computers or input computers too. Okay, let me know what questions you have now that we've gone over it fairly quickly and fairly briefly. We can talk about it more in class, but hopefully this gives you a sense of what those graphing problems were like. Thank you for your patience with this medium quality video. The production value is pretty low today, but I appreciate your patience. Take care. Let me know what questions you have, and I'll see you next time.